Welcome to the third day of XConf India 2021. Today we have a couple of sessions lined up. One is a keynote from Chris Ford, and then we'll talk about what he's going to do in a minute. And the other one is followed by the speaker launch that we're going to have. It will be a very informal session. You can ask questions and talk about that. In the time of crisis, pandemic time period, many people go through tough times. Tough times are not just physical or medical or financial emergencies. Many times it is psychological and emotional. Today, personally, for me, as well as for many others, music has been a big healer. So in the time of pandemic, listening to music, playing music, understanding music, it's a big healing for me. Today's talk about is also about music, as well as functional programming. If you are interested in any one of the subject, this is the right time to be in the right place, I guess. And functional programming being the right fit for the problem like music or to structure music. So people, please join me in welcoming Chris Ford, Head of Technology, Thoughtworks Office, Barcelona, Spain. And he is a principal consultant, speaker, architect, technologist, great musician, and a good friend. Welcome, Chris. Welcome to the.
Thank you very much, Shankar, for your warm welcome. And thank you everyone for coming. Yes, for me too, music is, it's just such a lovely subject to think about and talk about endlessly. I think what I love about it is that you can engage with it at any depth, right? So maybe you can be doing programming or you can be doing your job and music can be on in the background and it will maybe lift your mood. Or actually, if you really want, you can get into it at great depth and investigate how it works or how it functions in different cultures or how you might write it yourself, and it continues to reward engaging at that different depth. So hopefully we'll go a little bit towards that depth today, maybe for some people who haven't ever studied the structure of music or looked at that before. One thing I do want to say, as the elephant in the room, whenever we talk about music, it's very common for especially people working in academia or especially maybe in Europe or North America to speak about music theory without qualification. Right, so they will say something like, in music theory we have either major or minor, right? And the trouble with that is not that it's untrue, but that it's kind of culturally absolutist. So it is true that the music of Western Europe is a really delightful music. It has all sorts of interesting theoretical elements. There's been some great works composed in it, including by Johann Sebastian Bach, who I'll be discussing the music of today. But it's not in some way the pinnacle of human achievement in music or any more sophisticated or interesting than Carnatic music or Hindustani music or any other kind of music that has a great history and depth. I think sadly, that truth that European music is not an objective standard by which all other music should be judged is not always appreciated or acknowledged in conversations about music. I think I remember reading the other day, there's a textbook called The Complete Musician, right? And so you think the complete musician, oh, wow, that has to have a lot in it, that book, if you're going to teach students the complete musician, right? It has to have hip hop, it has to have, Latin American music, it would have to have traditional Japanese music, it would have to have Carnatic music. But actually, no, the complete musician apparently is someone who understands 18th and 19th century European music. And that's clearly just absurd, right? You wouldn't say that for any other aspect of culture about, literature or poetry or anything else, but it kind of still gets said a little bit in the Music Academy. So I'm going to talk about, I guess, slightly hypocritically, a music theory that is based in that tradition, where I think Johann Sebastian Bach is a really great example. But please let me say up front that while other musics will have similar structures and theories or so their own different departures. I'm not trying to imply any way that this is the music theory, just a music theory and an example of how you might analyze music in general, not that that every kind of music that you might love and enjoy works exactly the same way as this. That's my big disclaimer, just to make sure that I'm not being culturally imperialist. I'm going to go a bit more further in that vein at first and show you what often gets described as music, right? So you could say this is music, but like you can't hear anything, right? Other than my voice going on about it. And that's because this is a notation for music, not music itself. Although if you speak to someone who plays in a Western orchestra, they might just use the phrase music for both of them. So this is a particular kind of notation designed to convey a particular kind of music for a particular kind of context. So I guess maybe a lot of people who've decided to come along to this talk might be well enough educated to know how this notation works. But just for those of you who don't, I'm going to give just a quick introduction to when a Western musician reads this, what do they see and why? So there's a lot of flourishes and angles and little extra symbols, but when it comes down to it, this is a graph. So on the vertical axis is pitch. So the higher the dot, each dot represents a note, the higher the pitch, the lower the dot, the lower the pitch. And on the horizontal axis is time. So the further to the right, the further on in the piece the note goes. So, this is a da, 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 da. Sorry, don't worry, I will not sing for the rest of the talk. But you can see that this, when it comes down to it, is a fairly obvious graphing of frequency and time. It's a graph of time and pitch. And this is a really useful way for people to look at music, because this notation was designed for a person sitting there with an instrument to read this notation in real time and know what the next note is coming up and play it immediately. So for programmers, this might be an interesting kind of DSL to think about, like what was its purpose and how does it work? So one of the interesting things about this is that it is a regular language in the sense of regular expression, right? There's no nested abstractions in this. There's no subroutine. So if you're a Java programmer or a Ruby programmer, you might want to tidy some of this up by extracting some logic into a separate function that you could hide away. There's no extra level to hide things away in Western music notation. Every dot just literally means one note. And if you want to say that someone has to play the same note many, many times, then you put many, many dots. There's no kind of nested abstraction. And that's a good thing, because this notation is designed to be executed on a particular kind of finite state machine called a musician, right? So the characteristic of regular languages in a computer science sense is that they don't have a stack. They don't have that kind of context that you have to store and then unwind to understand something. So that means you lose the abstraction, you lose the ability to create function calls or specific things, but you gain the guarantee that you don't need to store an infinite amount of memory of context of where you are in the middle of the music. You can just look at the next note and play it. And so if I'm sitting there in the orchestra with my violin, I don't want to have to evaluate the thousands of nested function calls that go into a modern JavaScript app. I don't have the cognitive capacity for doing that. I just want to look, okay, what note is next on the page? And then I'll play that next note. Glossing over a little bit of detail, I guess you could say there's a little bit of state, like for example, there's ways of describing in a particular bar that you're moving to a natural version of a note rather than a flat or sharp version of a note. There is kind of some edge cases to this, but in general, what happens is you see a note, you play it. And that's great, but it makes a whole bunch of assumptions about what kind of music you're playing and what kind of things are important about the music you're playing. So this notation is not very good for notating beats, for example. So it kind of implies that you're in a notation where you're in a music where beat isn't the important thing to tell the musician. So every kind of notation or every kind of DSL, by being a simplification, necessarily makes some choices about what things are important and what things are not important. And because this is a non-extensible DSL, the only way you can get a new symbol to appear on this is kind of to run around all the universities in the world and convince them that your new symbol that means, I don't know, hitting the violin with the stick. The only way to get that to happen is to just upgrade all the clients, all the readers of this language. There's no way to define these extensions within a language. So I think this notation, because it's really awesome and elegant and successful, contributes to that kind of cultural imperialism or cultural complacency I mentioned earlier, where I said that for many people in the music academy, European music from the 17th and 18th centuries is the standard by which all other music is judged, because this notation is designed to really represent that kind of music well. And while it can represent other kinds of music, it doesn't always do it well. The sad thing is you can't extend this notation to add those concepts for those other musics as you see fit, because it's this kind of regular notation. So this is all a very long preamble to introduce my theme today, which is using code to represent music. So there's a little bit of a niche subculture of programmers who like to make beeps and bops of music using code. There's various reasons we do it, including programming being our hobby. And so we like to use programming for everything. But it's also because when you're programming, you do have that ability to create new domain-specific concepts and features. You do have that ability not just to use a language, but to work within a language, to shape a language and extend it. And I find that a really fascinating way to approach music. I don't think you're going to be seeing orchestras retired and replaced by programmers. I don't think this is like another software is eating the world situation where we won't need musicians who have great skill anymore. But I do think that the process of using code to represent music is another extra awesome angle, and it's particularly good for teaching concepts about the structure of music, because programming and code is all about structure. So what I've got here is a REFL hidden behind Vim. So Vim, or VI, depending on how you pronounce it, or Vi, it's just a regular text editor. And what I'm doing is each time I run a command, that command is being executed in the background. And it's being executed using the Super Collider synthesis server. You don't really need to understand that, but that's what's happening. That's why I'm typing stuff and stuff's happening. I might just quickly introduce how Clojure works. So Clojure is a functional programming language. So I think it would be great, like Shankar said, his introduction for people who love functional programming and music. This talk is a combination of interests. So Clojure is a Lisp, which means it's a functional programming language that uses parentheses everywhere to say what's going on. So in a sense, it's one of the simplest possible syntaxes for a programming language. So if I type this, it looks a bit weird because normally you would put the plus in the middle. But in Clojure, the function always goes at the start. And you can see if I executed that, I was able to get 2. If I want to define a function, def add 1, it takes an argument x. And so again, you just use parentheses everywhere. Oops, defen. Okay. And then I can just see the result up there. So it takes a little bit of getting used to and wrapping your head around. I guess also like the dots on a page, Western music notation does as well. But rest assured, there's not really much more complex going on than just each time there's a set of parentheses, evaluating and applying a function inside that. Cool. All right. So let's get a bit further into it. So one of the things that is very common from different musics across the world, because it is related to the physical phenomenon of sound, is sine waves, right? So that wave that follows the trigonometric function that goes up and down. And the reason why it's relevant to music is that sound in the air is a pressure wave that follows the sine pattern. So it's not like an ocean wave. So an ocean wave, if you put a cork on the ocean and you watched it, it would be going up and down. With a sound wave, what's actually happening is that the atoms are moving backwards and forwards between the source of the sound and the receiver of the sound. So what is going up and down is pressure rather than the height of atoms. And the interesting thing about thinking about it that way is that all the different musics in the world, in the end, are reduced to combinations of pressure waves that are happening at the same time. So if you can really understand the pressure waves well, it gives us a basis to build on top of to understand the whole of a music. So what I have here is, hopefully you'll be able to hear some actual executed music sound, is that this function defines almost the hello world of music as code. It just says, define an instrument called tone. And how does that work? Well, it takes one argument, which is frequency, which defaults to 440 hertz, and it just creates a single sine wave that activates that. Oh yes, thank you, Shankar. Longitudinal waves rather than transverse waves. Good, I'm getting extra terminology added in the chat. By the way, if you do want to make comments, I do watch the chat as I'm doing a talk, so feel free to heckle or suggest things or correct me that I've missed things. Anyone. So if I just make this tone, maybe I'll make it as 440 hertz first. Hopefully you can hear that, right? And let's just keep going, right? That's really boring. Sorry, let me stop it. So that was a sound. That was the longitudinal waves that Shankar mentioned in the chat, moving at 440 times a second. That's what defines the frequency. If I were to go back to doing it 300 times a second, it's a lower sound. And you can go down to very low sounds. The kind of outer limits of what frequencies we can hear go between about 20 hertz and 20,000 hertz. And in particular, the high end of the range is something that young people can hear that older people can't. So I don't know if you ever had a situation in your house where there was some electronics that was making really high noise and you could hear it, but your parents couldn't. Well, that's probably because over time, the range of hearing above 10,000 hertz to 20,000 hertz diminishes, sadly. And so I, for example, can't reliably hear sounds in that range anymore. So other than if you're really into Japanese drone music, having sounds that just continue forever is probably not that exciting. So I'm going to introduce one extra concept to make our first notes, which is the idea of an envelope. So the idea of an envelope is that it is a shape around the sine wave that makes it specific to a point in time. So a normal envelope will kind of start closed, open up, which is called the attack. So that's as the note starts and gets loud, gets to its maximum loudness, and then shuts off again. So what I have here, our kind of second most simple thing, beat, is that we have an envelope that just starts at maximum loudness and goes straight down. So this, I guess you could say the frequency of the sound wave is how high the pitch is, and the amplitude is how loud it is. So if we have the amplitude go from maximum to nothing, that means that the note will fade out. So if I play beep, it doesn't go on forever, it makes a note. And again, I could, play beeps of different lengths. And maybe even I could control the duration and have a really long beep. Maybe I can even play some notes that overlap. They sound nice together because the relative frequencies have a simple ratio. Cool. Yes, thank you, Kiran. It's basically the pitch in terms of music. Yes. Although the distinction I might make is that as programmers, I can probably explain this in terms of the networking model, right? So you have different levels in the OSI networking model, from kind of like, the basic, ones and zeros, the physical layer, and then you have high abstractions as we move up. So what I'm going to do is start to move a little bit further up the stack and add some more abstractions on top of this basic physical layer. All right, so that's sine waves. So harmonics are the next thing I want to introduce. So the sounds I produced so far are really simple because they only have one kind of sine wave in them at the one time. And it turns out that real sounds are a little bit more rich than that. And that includes instruments from all musical traditions. This is still something that's a characteristic of the objects we encounter in our real world. So it turns out that a real sound will have one frequency that's the dominant one, but it will also have another frequency in it which is double the first one, and triple and quadruple and times 5. So if you've ever encountered in mathematics, the harmonic series, that's why we use the word harmonic both for music and for that mathematics. So what we have here is a bit more of a complicated synth than our beep. I've called it Bell. And so it has the harmonic series in it. So it has the, the original sound, and then double it, triple it, quadruple it, times 5, times 6. But you can also see, if you look at this line, which says the proportions of loudness of these different frequencies, that it's the base one, H0, that's at 1. And then as we go further down, it gets quieter and quieter. So let me play the bell sound for you. Let me play the beep again, then I'll play the bell. So this is beep. Kind of okay, but it's like, the elevator has arrived at your floor. The bell sound. But it sounds richer, right? But it still sounds a little bit electronic. So there's an extra improvement that I'd like to make to it. So I told you what the ideal was, which is that the harmonic series is exact multiples of the base frequency. But it turns out that different instruments, what gives them their life and their color is that different instruments are unideal in their own way. So it turns out a bell, actually, rather than following the pure harmonic series, most bells, when they come to their higher harmonics, they're actually kind of quiet, but still there. They're sharper than they should be according to the harmonic series. So if I just reevaluate that, and I play the bell again. All right, that sounds much more like a real bell, and we haven't really done very much so far. Yeah, I mean, obviously I've cheated Sarah, and I've chosen an example of an instrument that I can define with a screen full of code. Different instruments will have different subtleties, but yeah, it sounds so much more realistic. We can, even play lowers or higher. Kind of nice. And what I love about this particular bit is that the beauty has come from what you might call the imperfection, right? The absolute ideal electronic sound doesn't sound as lovely as the one where we have, changed it or modified it a little bit. Cool. All right, so that's harmonics, right? Another thing I want to mention, it's called Psychoacoustics, which is a little bit of a fancy academic name, but it is about the fact that there is a listener involved in music too. And our perception of sound is important to the final result. Yes, I can say, yeah, Prashant, yeah, there's a lot of maths and physics, but I'm going to move and say complicated as well, and say that there's biology, because how the receiver of the signal, the human being, it responds to the signal is quite important. And here's a simple example of it, but there's many, many more examples. So I'm gonna play a couple of bell sounds. So the first bell sound is going to be at 600 Hertz, then down to 500, then down to 400. Right, so it's high, medium, low. So you're hearing that high, medium, low, partly because I primed you to hear that. But what's interesting about what I'm playing here is that I'm using my control of the harmonics that are built into the sound to actually cancel out the bass frequency, the bass frequency of the middle bell. So that means that the 500 hertz sound is actually 0 volume, and the first sound you hear is 1000 hertz, right? And I'm canceling out the first 2 harmonics of the 400. So the first frequency you actually hear here is 1200. So while you hear it as high, medium, low, actually what's happening is it's kind of low, medium, high. It's going in the opposite direction to what you might think. And the reason why this is a kind of a reliable illusion is because the idea of this harmonic series and sounds being built out of stacks of frequencies that are multiples of the base frequency is something that is still a physical reality and a biological universal. So your human brain knows that if it sees a bunch of frequencies in a harmonic series, it knows what the base frequency should have been, and it kind of puts it back in your mind when you're processing the sound. So if we were purely to go by the kind of naive physics of what's the lowest frequency in the signal, you would think that the music would be low, medium, high, but actually you just hear it as high, medium, and low. And this is kind of important when making electronics and so on. So you might even have if you have an old mobile phone or something, it might not be able to reproduce the base frequency of a human low voice. But the people who make these small speakers know that so long as they reproduce most of the sound, our brains can fill it in. Cool. By the way, I know this is a programming conference. And I know this talk is just not going to be about programming, but it's going to use programming. So that's the distinction I like to make. So I love to talk about just programming for programming's sake and how we can be better programmers and talk about code for code's sake. Sometimes I think that that should not be the only subject in the world that we talk about as programmers, and that it was as if a poet only wrote poems about writing poems. Sure, there's some great poems about writing poems. But also there are other things in the world. So that's my philosophy when writing these music talks. Cool, let's keep going. All right. So equal temperament. There's probably some music nerds in here. I'm not going to get into debates about different kinds of temperament and so on, but you can ask questions about it later if you want. But I'm going to assume that equal temperament, which is one of the things to come out of the Western music tradition, is what we're talking about here. So if you think about like a piano keyboard, there's lots of notes, black and white notes, and they're laid out in a repeating pattern. So it turns out that in almost all musical cultures, I think there's not been any reliable exception to this developed. If you double the frequency of a note, it sounds like it's equivalent. So it's kind of in a sense like 10 a.m. one day and 10 a.m. the next day are kind of the same in some sense. I guess that's convenient because doubling everything has a simple mathematical ratio. It also kind of accounts for the fact that in the human population, especially between typical male and typical female voices, there's a spread of double frequency. So it allows people to sing the same note, even if they're not singing exactly the same pitch. So it turns out that you can't just sing any frequency and expect it to sound good with other frequencies. So that the piano has buttons on it, right? It doesn't have a slider, it has buttons. So what defines those buttons? Well, it turns out that you can divide the octave into 12 evenly spaced sections, and that's where you get all the black and white notes. So I can represent this mathematically, probably better than my hand waving, by saying that I can convert from MIDI. So MIDI is a way of giving each piano key its own number to the actual frequency by using the mathematical power of 2. So the 12th root of 2, which is kind of a number that's quite close to 1. If I multiply the frequency by the 12th root of 2, it'll go up 1 semitone from one of these buttons on the piano to the next one. And then if I multiply by the 12th root of 2 again, it'll go up by another button. And ultimately, if I do this process 12 times, that's when I get through the whole octave. So if I, for example, calculate MIDI to Hertz of 69, that's the famous concert A of 440 Hertz, just kind of the example everyone uses, or really close to 440 Hertz with a bit of rounding error. So the reason that's useful is I don't want to have to remember the exact frequency of each note I want to play, because most of the frequencies on the spectrum are not relevant to my music. I want to be able to just give a number to each piano key so that I can abstract away some of that, that detail and avoid the possibility of playing notes that don't exist in my system. So I can play here is, this is a function called ding, which will go up the stack a little bit and allow me to play in terms of MIDI notes instead of the frequency, and will then just do that 12th root of 2 calculation for me. So if I ding 69, you get this. If I ding 70, each time I go up 1, it's going up an adjacent note on the piano keyboard. I guess if I were to go up by 12, it's like somewhere, the start of somewhere over the rainbow. It's moving up an octave. I know I promised I wasn't going to sing, but I forgot. So where, and this is great because as a programmer, I can start to accumulate these abstractions to make it easier for me to express my intent, just like maybe you do when you write your own JavaScript, Ruby, Scala, and things like that. And just to remind you again what's going on, the reason this is turning into sound and not just outputting as a number on the screen is because the Super Collider synthesis server is running in the background, and all my commands are being translated there. So to get back to this visualization of dots on a page, thanks, Sam. You'd love to hear me sing. Maybe when I'm warmed up a bit, give me a few years to take some lessons. Is that the dots on a page have both pitch and time. So we've talked a lot about pitch and frequency so far, but we also have to think about when the note happens if it's going to be a melody. So, and excuse me for having a little bit of code here. The conceit of this talk is that I'm defining all the code that you need to play the examples in front of you. So while it's a bit messy, but hopefully it's understandable to people who are interested in code. So a note has both a timing and a pitch. So what I'm doing here is just a simple constructor that just creates this little data structure that has 2 elements, timing and pitch. I need a couple of helper functions to express some concept in music. So where is like a special map function that maps onto one of these things in the map. So I can say, where pitch and then some transformation. We'll apply the transformation to every pitch in a melody. The other thing I need is from. So all from does is add a certain offset. So if I say from 1, that's equivalent to the classic plus function. All right. And it turns out that a lot of concepts in music can be represented as either this kind of adding the same number to everything, and also this where, which is applying a transformation to a particular aspect of the music. So now we get to a function called play. So it's looking a little bit like we're getting closer and closer to to concepts you'll actually have heard of music and not just beeps and bops. So what play does is play takes a list of notes and it says, I want to play them now. So it says, take the notes and take each time of the notes and offset it from now. Hopefully this line of code, if you think about it carefully, I know that a lot of you haven't seen Clojure before, but hopefully you can at least trust me that this is how it works. So this says that scheduled notes are the same as notes where the time is offset from now. So we move it. So what this thing does is it says for each note in scheduled notes, take the millisecond and the MIDI, and at the particular millisecond time, ding the bell. And so even melody is a maybe slightly simpler function. So it plays notes, but it plays the notes with every note being the same time apart, so a third of a second. So let me stop describing sound and actually just show you. So this even melody function uses the play function to play the range of MIDI notes from 70 to 81. Right, so it sounds a little bit like someone just going to a piano and just playing every note in turn, or if they have a bell set, I guess, playing each of them. And again, if I were to use slightly different numbers, you would get a slightly different result. Everything's a little bit higher. Right, so this still doesn't quite sound like real music, right? Because we're just playing every note next to each other. I need to introduce one more concept, which is the concept of scale, which is one of the basic and fascinating concepts. And this does apply to Hindustani and Carnatic music, though the scales themselves will be slightly different and the usages of the scales will be slightly different. So maybe I'll start by just looking at this definition of a major scale, right? So because what I'm doing is functional programming, I want to use a function to represent a major scale. So what I want to be able to do is tell it, the program, which note of the major scale I want to play rather than which note in the piano. Because it turns out, and the basic concept of scales is that though you have all these buttons on a piano, only a subset of those buttons is relevant for a particular piece of music. So that's what the difference between G minor and F major, that there are different subset of the buttons on the piano that you're playing for a particular piece of music. And by choosing a different subset, you're going to get a different effect and a different feeling of music. And they work in different ways from an artistic point of view. But in the end, they are all subsets of the same overall notes you can play on a piano. And that's why you can play music in lots of different keys using the same instruments. So what the major scale is defined by is, you can see it is defined by the number of jumps you need to make to get from the first note of the scale to the second note of the scale. That's a double jumps. That's one double jump, one double jump, one single jump, double, 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 single. So this just pattern of whether you're going to the next note on the piano or whether you're skipping over one note is what defines a major scale. So let me just execute some code to show you. So if I say, what's the 0th note of the major scale? Well, that's just 0 because that's our starting point. If I say, what's the 1 note? That's 2 because we've done a double jump. What's the 2 note of the major scale? Well, that's 4 because we've done 2 double jumps. What's the 3rd note? It's 5 because we've done 1 double jump, 1 double jump, and 1 single jump. So basically, this function is quite a simple numerical function. It's just I'm giving it a rank of a scale, as it's called, and it's adding up all the jumps I need to work out which note I'm going to play. So all I need to define C major is the major function that knows how many double jumps and single jumps to apply. And also the C bit says, where do we start this process of doing the double and single jumps? So that's using our function from it is from 72. So if I go down, maybe I can try playing something. Let's play C major as an even melody. And I'm just going to play a scale like you might practice an instrument. Cool. So that sounds a bit more musical than before. So if I start changing these things, I'll get something slightly different. So let's say D major, starting at a slightly higher place. Try E major. All that's happening is the starting point from when we start calculating these single and double jumps is being shifted. Now, there are lots of other scales you can play, and I'm only listing some of the scales here. So a minor scale works almost exactly the same as the major scale, except that the pattern of single and double jumps is in a different order. What's really interesting to me is how much of a difference that makes. So let me play the major and I'll play the minor. All right, and let's play the minor. Now, it's not really in the physics of it, probably the second one, depending on what kind of music you listen to at home and for fun. Probably the second one sounds a bit sadder, so I'll play it again. There's other scales as well. Like I really like the blues scale. Oops. The blues scale, I know that it's not normally played on bells. It's normally played on like slide guitar and things like that. But this is the scale used by that kind of the blues music of the American South. And the difference of that to others is, again, the pattern of double and single jumps. So if you're someone who knows musical jargon, it's these single jumps here that define the fact that we have the flat 5 in between the 4th and the 5th. Now let me try a pentatonic scale, as it's often known. So this is almost the same as the blues scale, but it sounds quite different. So it's the same if you look at let's just isolate here. If you look at the patterns here, they start with the same like 3 and 2, but the thing is the blues scale splits this double jump into 2 single jumps. So it just adds an extra note. So what I love about this is that the pentatonic scale and the blues scale have completely different connotations in modern world music. The blues scale is the American South, the pentatonic scale is probably most often associated with East Asian music. But the only difference is that we've added this extra jump in, this note in, and this extra jump is just like, in terms of frequencies, is the 12th root of 2 different? Because if you think, Max, earlier when we were talking about what defines the gaps between the different notes of a piano, it's the 12th root of 2 frequency difference. What I love is that therefore, if I play the pentatonic, and then the blues, it just has such a different connotation. Though the physical or mathematical difference between the two is not very different. I guess it just shows that we are musical animals. We do have the ability to distinguish very precise differences in sound, at least within 20 to 20,000 hertz. Cool. Cool. Yeah. It sounds like if you want to get some more advice on tuning systems and intonation, Anshuman is in the chat talking about that. So feel free to nerd out, people who already know quite a bit of music theory. Right, so we've talked about the time and the pitch. So let's put it together, which is normally called melody, right? So melody is a chunk of notes that have defined times and pitches. So Row, Row, Row Your Boat is a well-known children's melody, at least where I'm from. And I can write it out in code, maybe a little bit awkwardly, using this, this little bit of code that just like sums up the times and puts together, basically by creating individual note data structures that have a time and a pitch. So let me execute. Oops. So this is kind of what it looks like when you define row, row, row your vote. And I'm not saying that this is easy to read, right? This is the machine readable version. But you can see that in the end, this data structure is just a bunch of things that have pitch defined and time defined over and over again. So there's one last concept I need actually before I can play it. And if you look at the time, like time 0, what's time 0? Or time is time 11, what's time 11? In order to define how fast the music goes, we need to just apply a transformation to each time. So the relative spacing of the times in the melody is fine, but we just need another function that I'm going to call BPM, for beats per minute, that's going to multiply each time value by a fixed amount, and that's going to define how fast the music is. So all that beats per minute does is it creates a function that will then multiply other things. So if I just execute beats per minute, beats per minute itself, that's just a function. But then if I say for beats per minute 120, where's the third beat? It'll tell me that it's at 1500 milliseconds into the song. So the reason I'm telling you this is that I'm going to use this BPM to turn Row, Row, Row Your Boat into a melody at a certain time, and then I'm going to use my C major business to put it in a certain key. So this data structure of Row, Row, Row Your Boat is independent of speed and pitch, and then we're just going to put it all together. I think the power of this is that it's true I'm describing what's going on. Because we can use programming to express these concepts, you can view source on it, right? You can look at the exact definition and you have to believe me that it's working because you can hear that I've executed the code and the right things happen. Cool thing about this is it gives us a bit of separation of concerns, right? So I can keep the melody written the same and I can make it faster, or I can make it in a different key and then play it again. Cool. So that's how I can start to use mathematical transformations to play with pitch and melody. But what I promised you at the start was that we need to be able to develop new abstractions that will allow us to represent new concepts in music as we need them. So in Bach's music, maybe I can just go back to this. You can see Bach's music has certain regularities that are common to Bach. So you can see there's like these sections of music where there's adjacent lines that all happen together. So you might think, well, it'd be nice if in my code I can see something that represents the fact that these notes run together. Just checking. Cool. So I can do that. And this is a little bit awkward code, but only because it's representing a slightly complicated concept, but it's representing the idea of run. So if I specify the idea of the troughs and the peaks, then this function will fill in all the notes in between. And the nice thing about this is I think it matches a bit closer how someone would talk about music to another musician. They wouldn't say, okay, you think that, you know, that piece in the music where it goes A, B, C, D, E, F, G, A, B, C, they would say, oh, you know that bit in the music where it starts on A and there's a run all the way up to the highest C? And so by creating these abstractions in code, we can get a little bit closer to the domain. So if you're into domain-driven design, then you can see where this is going. So if I define a run that starts on the root of the scale, goes up to 4, goes down, goes up a bit, and goes back, then when I play it, it'll sound a bit like this. Cool. So that sounds a little bit more like Bach-like music, I think, if you're familiar with Baroque music, all these like elegant runs where there's adjacent notes. Cool. All right. So I'm going to start to move into the Bach because I said that I was going to talk about Bach, and I really like Bach, and I think it's cool music to understand. And the nice thing is it's kind of mathematical, so it works well for programming. So what this is here is this is music that represents the same as the first bit as this, right? So I guess dots on a page are hard to read if you don't know it. Code is hard to read if you don't know it, but in the end, it's a specialist notation that serves a purpose. So actually, let me just print it out. Okay, so there's a lot of notes here, and I don't expect you to read this directly, but basically, it's like there's a data structure with a time and a pitch for every dot in the Bach's notation. So final concept that I want to describe, which I think is really cool, and this idea of canon, this is the ultimate example of a musical idea that is not universal, right? So I'm going to explain what it is, but this is not something that you should expect to see in all musics everywhere. This is a particular cool feature of music from Bach's day that actually became unpopular soon after that, sadly. But what's awesome is that even though this kind of musical idea isn't really alive and used today, we can describe it using code, and we can discuss its structure. So what is a canon? So I've got this quite succinct definition here. I think in Clojure, I hope this makes sense. So a canon is when you have some notes and you put those notes together with a transformation of those same notes. It's a little bit abstract, but what I really like about this is that it's a higher order function. Basically, it takes F, some transformation, and says that a canon is the same notes repeated, but sorry, two versions of the same notes, but one that's differed by some transformation. So that means that you have different kinds of canon depending on what the transformation is. So a simple canon, as you know, this is what you'll find it in Wikipedia, is where you use a transformation where you take the notes and then you say where the time is delayed from wait. So the second version is delayed in time. An interval canon is structurally very simple to a simple canon. In fact, you look at these definitions, they're the same except for one key difference, which is that an interval canon is in pitch. So an interval canon is when the second version of the notes is up or down from the first version of the notes. And then you get all these like cool other kinds of canon, like a mirror canon is where it's like you've looked at it in a mirror, you've flipped the melody vertically. So it's a mirror image of itself. A crab canon is where you play a canon backwards, right? And it's called that because in the Bach's day, for some reason, they thought crabs walked backwards rather than sideways. I guess they didn't have crabs at home. They didn't know that that's not quite right. What I really like about this is these definitions of a canon might take me a long time to talk about in natural language, but hopefully you can see that the code definition is quite succinct. So a mirror canon is where you take the notes and you multiply each pitch by the minus sign. You flip it. Crab works exactly the same, but for the time. So things flip in the other axis. You also get cool property of canons is that they're composable, like functions are composable. So you get canons where the transformation is made up of several of these other transformations at once. So a table canon is the functional composition of a mirror canon and a crab canon. And the reason it's called that is because you imagine a piece of music, like the dots on a page, sitting on a table between you and a friend. And if you both play what you see, the person on the other side will play the notes flipped in both pitch and time. By the way, you can see this is really complicated and hard to write music in this form, and that's why possibly pop music today doesn't use these forms. So just moving quickly towards the final example. So Row, Row, Row Your Boat is a canon, but it's a simple one because we want kids to sing it. So that's when we have multiple copies of the melody, but the second copy is delayed in time. So if I play that. Cool. So that is two copies of the same melody, but the second one is delayed. And I don't know if you've ever seen teaching kids to do this. It's really fun. You tell one group of kids to start singing, and then after a moment, the second lot joins in. Cool. So I'm going to get to the really awesomeness of this piece of music by Bach, right? So it turns out this is a canon, and if for people who are really cunning at noticing, you can actually see this is called Canone alla Corta. And it's a really, really intricate and I think admirable piece of music. So how does it work? So I can describe it. Canone alla Corta, the transformation of the notes, has 3 composite transformations inside it. So it's an interval canon. So the second copy of the notes goes down by 3 notes. It's a mirror canon. So the second copy of the melody is flipped. And it's also a simple canon, which means the second copy of the notes is delayed. So let me quickly zoom in on this. So you can see, if you look at this bit of notes here and this bit of notes here, they have the same shape, but this one is upside down, dropped, and delayed. Now, I will play this music, but it is not at all easy to compose music where doing this transformation business sounds good at all. But Bach is famous for a reason, and he managed it. So I'll play the melody without the second copy at first, so you can hear just how complicated it is. Cool. So I think that's just amazing on its own. But now let's play it with the Canon transformation, which is just a functional transformation defined on this line. So we get 2 copies of the melody that sound great together. I'm going to make one more pitch for why music as code is really awesome, which is that we can do other things to music once we have it in a logical form, like, for example, graph it. So let me slow this down just a little bit, and maybe I'll just change key because that's fun. Right, so you can see this is just a direct graphing of the data structure, how we've got this pattern here. That's the same as this pattern here. And that's what makes a canon, which is a very famous Western musical notion because it's so beautiful and elegant, but also, I should warn you again, is not a universal musical concept. It's something that arose in a very particular place and time, but I think it's, despite the fact that it happens to be from the one of the kind of the loudest and dominant musical culture of the world, also something that's really beautiful and worth understanding. And what I think is great about music as code is, unlike Western music notation, where we have dots on a page, this concept of using code to express the logical structures is available for all musical cultures. That if you wanted to express concepts in Hindustani or Carnatic music, in this technique you could. If you're one of the people on the chat who understand music theory deeply, for example, you could do it for all kinds of music around the world. So even though I know that sometimes code is a homogenizing force that can seem like it creates a single world culture and minority cultures get stomped away, what I really hope is that if we apply music to creativity, code to creativity in the right way, we actually can really show respect and respect the diversity of culture and music across the world. Thanks very much.